Okay, so today I want to wrap up the proof of the optimal lower bound for Johnson-Lindner-Strauss. I apologize that the lecture notes didn't go up right away, but I did put them up yesterday. And then once we wrap that up, I'm going to talk about how to speed up the actual time to do the embedding in a JL embedding. So let's first wrap up the JL lower bound proof. And I just want to walk over this. This is stuff that we talked about last time, the key takeaways that we can continue. So remember that the whole way the proof is organized is we don't just have one point set, but we have a collection of point sets. And we're going to show that if it's true that every point set in the collection has a low distortion embedding into low dimensions, then we have an injection from that collection of point sets into a smaller set, which is a contradiction. Okay. And what is this collection of point sets? It's actually ordered point sequences. And if the endpoints are 0 together with the D standard basis vectors, EI means you have a 1 in the ith position and 0s elsewhere, together with ys1, ys2, etc., up to ysn minus d minus 1. So you have exactly n vectors. And ys is the indicator vector for the set S, okay? Appropriately scaled to have unit norm. So S, as I say here, S has size K, that's right here. Oops. S has size K, and K is this 1 over 100 epsilon squared. And the indicator vector of S means you put a 1 in the ith position if I is in S, you put a 0 if it's not in S, and then you scale it by 1 over root K so that it has unit L2 norm. So 1 over root K is 10 epsilon by my choice of K. So entries in YS are either 10 epsilon or 0, depending on whether or not I is in S. How many possible point sequences are there? Well, the first D plus 1 are fixed. The next n minus D minus 1 could be arbitrary. So there are D choose K choices for any given S. Raise that to the n minus D minus 1 power, because that's how many S's you're choosing. And then the logarithm of that is, just roughly nk log n, okay? If you assume that D is n over log over epsilon, which I'll show how to remove that assumption later. Okay, other things I want you to remember from last lecture, we talked about entropy numbers or covering numbers. So basically you have a set and you want to take an epsilon net of that set under some norm, okay? How small of a net can you come up with that achieves this? So we had one argument via packing and a volumetric argument via packing that showed that if you take the unit ball of any norm, okay, and try to find an epsilon net of that unit ball under the same norm, then the number of net points you need is at most roughly 1 over epsilon to the D, O of 1 over epsilon to the D, where D is the dimension. Okay, good. Okay, so now the name of the game is, right, we're assuming that every point set, capital X, in script X, every single point set has some low distortion embedding. And as we saw last time, low distortion embedding means you preserve dot products up to an additive epsilon. So for a given point set X or point sequence X, there is this embedding F. I should really call it F sub X because it depends on X. Okay, such that all the dot products within capital X are preserved up to an additive epsilon after you apply F. And if F embeds into dimension M, I want to show that the fact that such an F exists for every point set in this collection means that there exists an injection from this collection of point sets into bit strings of length nm, which implies, of course, right? This implies, this implies that nm is omega log the size of x, right? Which is omega nk log n. And then you cancel the n's and you get exactly what you want. M is omega k log n. And right, what is k? K is roughly 1 over epsilon squared. So you get a 1 over epsilon squared log n lower bound. Okay. So now the question is, what is this injection? Okay. So take one, which we actually talked about last time, is you look at f applied to all of these points, f of 0, f of e1, f of ed, f of ys1, f of ys2. Now these are m-dimensional vectors each, and the entries are real numbers that have infinite precision. But you know that, all of these vectors originally had unit norm. I mean, 0 has 0 norm, but the rest have unit norm. After you apply f, their norm is at most roughly 1. It's at most roughly 1. It's at most 1 plus epsilon, right? So these are still roughly unit norm vectors, which means that no entry in the vector can be bigger than 1 in magnitude, basically, right? Or bigger than 1 plus epsilon in magnitude. So all the entries in each vector after you apply f are roughly between -1 and 1. So what we're going to do is we're going to discretize the interval from -1 to 1 into integer multiples of gamma. So think of gamma as some very tiny thing, like 0.01, right? So I'm just going to say, look, there are these discrete points there. There's 0, there's 0.01, 0.02, 0.03, 0.04, all the way to 1.00. And whatever my entries are, I'm just going to round them to the nearest multiple of 0.01, or I'm going to round them to the nearest integer multiple of gamma. So gamma is 0.01 here, okay? So now, after I do that, I claim that there's still enough information to, based on these rounded versions, there's still enough information to figure out what the point set was, or what the sequence of points was. Why? Because before you did the rounding, if you just look at all the EIs dotted with the YSJs, knowing all those dot products told you what all the YSs were, what all the S's were. Because if a dot product is 10 epsilon, I is in S. If it's 0, it's not an S. After you apply F, it's either going to be between 9 and 11 epsilon, or it's going to be between minus epsilon and epsilon. But still, there's a gap. It's either going to be at least 9 epsilon or at most epsilon, or at most 2 epsilon, sorry. At most epsilon. So there's still a gap. And then the claim is that even after you round the entries up to add it to integer multiples of gamma, there's still a gap. And why is that? So let's look right here. I'm taking these vectors and I'm imagining that I'm rounding the entries to the closest multiple of gamma, and then I'm taking the dot product. What does that new dot product look like? Well, it's the sum over I from 1 to m of that entry plus or minus the error introduced by rounding times f of yi plus or minus the error introduced by rounding. Then you just use the distributed law. This is equal to the actual dot product I cared about plus or minus some error terms. So I have terms that look like gamma times in magnitude at most the absolute value of f of xi summed over I. So that's basically the L1 norm of f of x. So I have an error that's at most gamma times the L1 norm of f of x. I also have an error that's at most gamma times the L1 norm of f of y. And then I also have gamma squared, right, from those other terms, the plus minus gamma times plus minus gamma. I have a gamma squared term, and I have that m times. So I have another error that's at most m times gamma squared. And now what I'll do is I'll use Cauchy-Schwarz, right? Cauchy-Schwarz says the L1 norm is at most square root of dimension times the L2 norm. So this thing is at most root the dimension times the L2 norm. Same thing here. This is at most root dimension times the L2 norm of x, f of x. Okay, and we know that the L2 norm is basically at most 1 or 1 plus epsilon, right? So this is now the actual dot product I care about, plus or minus, roughly 1, so plus or minus O of root m times gamma plus m times gamma squared. So if I choose, I can choose gamma. I'm choosing what precision I'm rounding to. So I'll just choose gamma to be something like, epsilon over root m. Okay, some small constant times epsilon over root m. And then this will be the actual dot product I care about, plus or minus an error term of epsilon. So before, the dot products were either less than epsilon or bigger than 9 epsilon. Now they're less than 2 epsilon or bigger than 8 epsilon. There's still a gap. And now how many bits does it take to write down a number? Well, there are only O of 1 over gamma numbers, only 1 over 1, 2, almost O of 1 over gamma multiples of gamma between -1 and 1. So that's log 1 over gamma bits. So log 1 over gamma bits per number, m numbers per vector, and vectors. That's basically the total bit complexity of writing down all the vectors after you round. And you know that that has to be omega nk log n. That's right what we said over here, right? Basically here, it has to be omega nk log n. The n's cancel. You can move the log over here into the denominator. You know, now gamma itself depends on m, so you're saying that m is omega something that depends on m, but you can solve that asymptotically. This implies that m is omega 1 over epsilon squared log n over log n plus log 1 over epsilon. So you do get something that's like almost right. It's just not quite right. So how do you fix that? So now let's do the new stuff. Any questions about that? I'll just maybe give you guys like 5 seconds in case anyone has a question about this. Okay. And this is everything I'm saying about the lower bounds today, including the stuff we didn't get to on last Wednesday, is in the lecture notes. So if you want to go through the calculations more carefully, it's all there. So let's do take 2. So take 2, we want to basically eventually we hope that we can get rid of this denominator here, because that denominator should not be there. Okay. So how are we going to do it? Take 2 is, look, we rounded to make sure that entry-wise we're always within gamma. Essentially, that means that we took an L infinity net of the sphere. So you know, we took the L2 ball, the Euclidean ball. We took an L infinity net of the L2 ball, and then we rounded points within this L infinity net, meaning that every entry was preserved up to this gamma. So now let's instead round to an L2 net. Suppose that, you know, I round so that f of x tilde minus f of x L2 norm is at most epsilon. Here, f of x is like closest point in an L2 net. Okay. Then what do I have? I have that if you look at f of x tilde dotted with f of y tilde, right? Because we're going to write down as our for our injection, we're going to write down the rounded versions. So the question is, from the rounded versions, do I have enough information to be able to distinguish the 8 epsilon from the 2 epsilon, right? Am I only changing the dot product by another epsilon? Okay. So I can write this as, I'll just basically add and subtract the same numbers that I basically get, 0. This is equal to f of x plus f tilde of x minus f of x. Right, so I just added and subtracted f of x. So this is still f tilde of x dotted with f of y plus f tilde y minus f of y. And then I can again use distribution and say, look, this is equal to what I want. It's equal to f of x dotted with f of y plus, and these are the terms that, are error terms. Plus, I have something like f of x dotted with f tilde of y minus f of y plus f of y dotted with f tilde of x minus f of x plus f tilde of x minus f of x dotted with f tilde of y minus f of y. So these other 3 things are the error terms. So let's say this is, the amount of error I add is plus minus the absolute value of this quantity, plus minus the absolute value of this quantity, plus minus the absolute value of this quantity. And then now I can do Cauchy-Schwarz again. I can say, look, this right here is at most the norm of f of x times the norm, the Euclidean norm of f of y minus f of y. And this is at most right here, again, similar at most f of y times the norm of that difference, etc. And same thing here. I can do this is at most some norm times some norm. Okay? And the point is now, if I take, let's say, a gamma net, not an L infinity, but a gamma net in L2, then by definition, this is at most gamma. And this is at most gamma. And in fact, this is at most gamma squared. Okay?
Did we not say it was at most epsilon?
I'm sorry?
Did we not say it was at most epsilon at the top? Or is that supposed to be gamma?
Oh, yeah, sorry. So, yeah, let's say it's, I mean, I'm going to set it to be epsilon, but let's see, let me be consistent with myself. It's gamma. Okay. So, and now what do I know about the L2 norm of f of x? Again, this is basically at most 1 plus epsilon. So this is, it's roughly at most, 1. And this is roughly 1 as well. So this whole thing is definitely, f of x dotted with f of y, plus or minus some, like basically O of gamma, right? Because I have roughly 2 gamma plus gamma squared, which is O of gamma. So I can set gamma to be, again, some c times epsilon. So that implies that this, again, is f of x plus dot f of y, plus or minus epsilon, which is exactly what I wanted. I wanted to basically be able to know the dot product up to an additive epsilon error. And now the question is, what is the size of this net? Again, all these points, these x's and y's of mine, these are the f of EI's and the f of YSJ's. They have norm roughly 1 at most 1 plus epsilon. Okay, so really what I want to know is like the size of the net. We want an epsilon net, basically gamma net, but gamma is basically epsilon. An epsilon net of the BL2M of radius, let's say 1 plus epsilon. This is the radius. So what I mean here is take the ball in the L2 norm in dimension M of radius 1 plus epsilon. I want an epsilon net of that. And basically by this thing over here, this is the unit ball. This is radius 1. But if you want to cover the radius 1 ball with, covering the radius 1 ball with like an epsilon net is the same as covering, the radius R ball with an R times epsilon net, right? If you scale up the ball by R and you scale up the net closeness by R, it doesn't change the covering number. It doesn't change the entropy number at all, right? Does that make sense? Because in the scale down version, if things are within epsilon of each other, then if you scale up everything by R, then now they're within epsilon R of each other. So, so the fact that we're looking at the 1 plus epsilon ball just means that we should scale up this epsilon also by 1 plus epsilon. Right? But epsilon times 1 plus epsilon is still basically epsilon. Okay. So, bottom line is that if you look at this, the entropy number of this ball, let's call this B, B prime because it's the net. B prime under the L2 norm with a quality epsilon, this is big O of like 1 over epsilon raised to the dimension, which for us is M. All of this is happening in dimension M, right? Because we're covering the f of x's, which are in dimension M. So this implies that to specify a point in the net, you have to tell me, which of these 1 over epsilon to the M points is it? That takes log of that number of bits. So that's like O of M times log 1 over epsilon bits to specify a net point. And there are n net points because there are n vectors that, that we're applying f to. So that's the total bit length of the injection. And that, again, has to be omega nk log n. And then you get cancellations just like before. So that implies that m is at least 1 over epsilon squared log n over log 1 over epsilon, right? So this, by the way, is exactly, there was a lower bound proven in 2003 by Noga alone. This is exactly his lower bound. I mean, the bound itself is the same bound he showed, but he did not actually use this argument. He had a totally different argument, which I'm not going to show you today. Okay. But it's interesting that this totally different approach happens to recover the same exact bound. So now what I want to show you though is take 3, which is even this log 1 over epsilon, I want to get rid of it. So we just have to, it's at this point we're almost there. We just have to kind of, there's one thing from convex geometry that we need to know. Remember I was talking to you about symmetric convex bodies and the fact that they're in correspondence with norms. We're going to use that now. Okay. But, you'll see we're going to use it in a very simple way. And now, the hard part is just a matter of writing down everything we know and then kind of leveraging as much as we can to get rid of this thing. I mean, so what are we going to do? Okay, so let's write what we know. Said that to, decode, whenever we do these compression arguments and I say like we show that there exists an injection, right? That injection you can think of as an encoder. How do you prove that it's an injection? You prove that you can invert it, namely that you can decode the output of it. Okay. So to decode, we just needed to know, basically EI dotted with YSJ up to some additive error of, let's say, I don't know, 3 epsilon for each, actually, we said 2 epsilon, I think. It doesn't really matter. For each IJ. If we know all these dot products up to this additive error of 2 epsilon, that's enough to decode. And how are we getting that? We were saying, look, we're saying take this dot product, like F tilde E1 transpose, so as a row vector, F tilde E2 transpose, so it's a row vector, up to F tilde ED transpose. So like put these as rows of a matrix. Call this matrix A. What are the dimensions of this matrix? It has D rows and M columns. And then multiply it by this guy. Let me give myself more room. Which is F of YSJ right, and let's just call this, this by definition, let's just call this VJ. So VJ is this D-dimensional vector. So what we said basically is as long as you know, and this should also be tilde.
Should be M-dimensional?
What? Which one?
F of YSJ.
Yeah, this is M-dimensional, that's correct. But VJ is D-dimensional. Okay? I guess technically I tilted the whole thing before, so these are all tilted.
Oh, VJ is the whole product, sorry.
VJ is like all the dot products. Yeah, there are D of them. So really what we're saying is like, we want to know VJ for each J. It's the same thing, right? Okay, so we said that as long as we know VJ for every J, we're happy, right? That's basically what we said so far. But notice that that even tells us a little bit more than what we really need, because we don't need to know VJ exactly. We just need to know VJ rounded to an L infinity net, right? So we actually only need to know some VJ tilde such that VJ minus VJ tilde in infinity norm is at most epsilon, right? Because what are the entries of VJ? They're either between minus 2 epsilon and 2 epsilon, or they're between 8 epsilon and 12 epsilon, right? That tells us whether or not I is an SJ. So if we know it only up to another additive error of epsilon, that means now it's between minus 3 epsilon and 3 epsilon, or between 7 epsilon and 13 epsilon. That's still those intervals are still disjoint. So we still can tell whether or not I is an SJ. Okay. Okay. And then here's the I guess the part really I think that is maybe the least the thing that maybe you wouldn't think of unless you know a little bit about this convex geometry thing to do is look, let's define a symmetric convex body. E is equal to the basically the column space of A. In other words, it's equal to the set of all vectors AZ, where Z is in Rm. This is a subspace of Rd. Okay. And the dimension of the subspace is at most M, because A has M columns. Okay. And now what I can do is I can define a symmetric convex body K to be equal to E intersect the L infinity ball in D dimensions of radius, around the origin of radius 12 epsilon. Okay. So it's the intersection of this L infinity ball, which is a cube. So it's some cube of like side length 24 epsilon in every dimension. And I intersect that with some m-dimensional subspace. So now what I have is basically a lower dimensional, an at most m-dimensional or a dim e-dimensional symmetric convex body, which is K. So this is a symmetric convex body of dimension at most m. And what do I know? I know that for all j, Vj is in K. Right? Because Vj is definitely in E. It's equal to A times some vector. And it also has L infinity norm at most 12 epsilon. That's what we said earlier. And now here's the magic. Rather than think about it as I want to take some L infinity net of quality epsilon in D dimensions, what I'm going to do is I'm going to take a K net of K, right? K is some set, it's a symmetric convex body. I am going to cover it in its own norm, okay? And I'm going to take a gamma net in the K norm. And what's gamma? Gamma is going to be a 12th. Take a 1/12 net of K in the K norm. Okay. And then I'm just going to say, look, V tilde is the closest point. Call this thing K prime. This is the net. V tilde is going to be the closest point in K prime to V and K. What do I know? I know that V minus V tilde has an infinity norm at most epsilon, right? Because K, the body, remember the K norm. I mean, another way to think about epsilon nets, instead of thinking about it as I want to take a subset of the points that covers everything, you can think of like I have this body K. And I'm taking versions of it that are 12 times smaller, and I want to cover it I'm going to cover it by translations of itself. So like, that's basically a square. I want to take smaller squares that are 12 times smaller, and I want to cover it with these smaller squares that are 12 times smaller. Does that make sense? So, right? So basically, the original square had side length 12 epsilon, or 24 epsilon, or whatever. And now these small red squares have side length epsilon, because I'm taking a 1/12 net. I'm shrinking it by a factor of 12. Does that make sense? Okay.
So this K is only like a convex body in this, like not in all of RD, but just of this m-dimensional
right,
subspace.
Yeah, exactly. If you view it as like in the subspace, it's an it's a dim E dimensional body in that subspace. It has volume in that subspace.
Yeah.
Right. So like the net points are basically the centers of these red balls, right? These are the net points. And I'm saying that everyone in the black square is close to one of these red points. And what's the distance? You know, if this black point is close to that red point, then it has to have L infinity distance at most epsilon, because that red box itself only has radius epsilon and L infinity. So now, what's the size of a 1/12 net of K in the K norm? And magic, we can use this thing again, right? If you're covering the ball of a norm in its own norm, then the size of the net is roughly 1/epsilon to the dimension. Okay, so that means that K prime has size, O of 1/112 to the dimension of the body, which is M, which is like O of 1 to the M. So that implies that to specify a point in the net, you only need O of M bits to specify each V J tilde. So this implies O of NM bits total. Yeah, and that's exactly what we wanted, right? Now you have NM is omega NK log N, and then you get exactly what I promised you. The N's cancel. M is omega 1/epsilon squared log N. There is a very slight issue here. There's a bug. So I'm going to be able to fix the bug on this slide, and I left some space open on the right-hand side. But does anyone see why there's a bug here? It's not totally obvious. Any takers?
I mean, you didn't resolve the D equals whatever thing.
Okay, there's that too. That's true. I didn't resolve that I set D to be something very specific. And notice I haven't even used it yet, right? I haven't used the fact yet that D is specifically N over log 1/epsilon. Why did I choose that? I mean, I did do, earlier on, we did have a log D over K somewhere, and I said, look, this is roughly log N because D is this. But, I mean, I could have chosen, there's a wide range of what I could have chosen D to be to make that part of the argument work. Why did I choose specifically N over log 1/epsilon? So let's just pretend for a second that we are the decoder, right? We're given the injection applied to the point set, and we need to figure out how to invert the injection. Okay. So what did the encoder do? The encoder.
Subspace is.
What?
You need to know what the subspace is.
Yeah, exactly. You need to know what the subspace is, right? So what did the decoder do? What did the encoder do? The encoder wrote down this matrix A, right? He said, let me define E to be the column space of A, and let me define this symmetric convex body K, which depends on A. It depends on that subspace. And then he rounded to a net of that norm. But the point is, the norm depends on the subspace depends on F, right? Because if you look at the matrix A, it depends on F. And F is actually really F sub X, right? All we know is that each point set has its own embedding. So F for this point set might be different for F for that point set, which means that the subspaces you get, the A's you get are different. So the decoder who's trying to decompress, you tell him, okay, V1 tilde is the 17th point in the net. He's going to say, what net? I don't know which norm you're using because I don't know which subspace was used in the definition of the norm because I don't know A, right? The decoder does not know A. So that's what we're going to fix right here. The encoder also writes down A. Okay. How many bits does that take? Well, A has D rows, and each row is a rounding in an L2 net, which is an epsilon net of dimension M. So D times M log 1 over epsilon bits. And then I used what D was. D is N divided by log 1 over epsilon. So this is, again, another NN bits. So, in total, I'm still only using O of NN bits. So that now I'm really not lying to you. That's the end. Okay. So now the decoder can actually decode. So now the question is like, what if D is not equal to N over log 1 over epsilon? So the easier case is that D is bigger than N over log 1 over epsilon. What if I want to show a lower bound in this case? That's easy. Just take the set of points that's hard. We just showed that there is a set of points that's hard. Take the set of points that's hard in dimension N over log 1 over epsilon, and just pad them with zeros until they have dimension D. You haven't changed anything about the points, about the distance structure. So if the original point set was hard to embed, this is just as hard to embed. Still just as hard. Case 2, what if D is less than N over log 1 over epsilon? Okay, let's say that X is the hard point set. X is hard. It's in dimension N over log 1 over epsilon. Hard meaning that it's a point set where you cannot beat JL. So what are we going to do to X? Let's just apply JL to X. The claim is that f of X is hard, where f is a JL embedding. So f of X has dimension O of 1 over epsilon squared log N. Right? And the point is, like, the proof, suppose not, suppose G maps f of X to some very low dimension, beating JL with good distortion. Then G composed with F beats JL for X. But that's a contradiction, because we said that you can't beat JL for X. You can't go into lower dimension for X than JL. Right? That was our assumption. Our assumption was that X is the hard point set. So basically what this argument lets you do is, this box basically says we can get a hard point set for any D which is at least some constant times 1 over epsilon squared log N. Of course, once D is much smaller than that, you're not going to be able to prove a JL lower bound. Why? Because you can just take the identity map. If the original dimension of the point set was 5, you're not going to be able to say, oh, there's no way to embed this 5-dimensional point set better than 1 over epsilon squared log N. No, you can just do the identity map. The identity map maps it back to 5 dimensions with no distortion whatsoever. Right? So, essentially, this is the best you could hope for. Okay. Any questions? Okay. So that's really it. You've seen everything there is to see about the JL lower bound. So now I want to talk about, phase 2 of this lecture, which is speeding up JL. Okay. And the original JL in 1984 is random projection. So what does that mean? You take a random m-dimensional subspace of RD and project there. How do you do that? How do you actually, if you want to actually like write code and implement this, how would you do it? Here's one way to do it. I basically need to take a random basis. So I need to take m vectors, or m random orthonormal vectors in RD. So how do I do it? My first vector, they're in RD, so they're d-dimensional. The first vector, I'll just take some random Gaussian vector. Okay, right? Gaussians are rotationally invariant, so I mean you're equally likely to get any angle. The direction. I mean the magnitude, the L2 norm of the vector is a random variable, but the direction it's pointing in is a uniformly random variable over the sphere. So you take this G1, which is ID Gaussians, and then you just normalize it by its norm. So you remove the randomness from its norm by normalizing. Now you actually just have a random point on the sphere. So there's your first basis vector. Now what you'd like to do is you'd like to take another Gaussian vector. Okay. But the problem is, of course, that it might have some, it might not be orthogonal to the previous one. So you just project that out. You remove its projection onto the first vector. So you dot it with the first vector. That gives you a coefficient. You subtract the coefficient times G1. So this is like the normalized version. And then you normalize by its norm, etc. So basically what you're doing is you take IID Gaussian vectors, identity covariance matrix in dimension D, and then you do what's called, Gram-Schmidt. Gram-Schmidt just means, you orthonormalize them. Okay. So what does that mean at the end of the day? This is going to be a dense, unstructured, and a random matrix. Which means if you look at the map, Z gets mapped to pi Z is super slow. And I should say, this matrix, let's call this matrix A. Then, eventually you're going to take M of them. Eventually pi is just going to be A transpose, maybe appropriately scaled. So that's the original JL matrix. I mean, I'd say super slow. I mean, I don't want to use superlatives unnecessarily, but I just want to say that Z to pi Z is is dense matrix vector multiplication. Which is like basically M times D time. You have an M by D matrix. It's dense, it's unstructured. You're multiplying it by a D-dimensional vector. That takes time, M times D. So, naturally there's a question here of, can I do that faster? Can I get the same kind of JL guarantee with a faster embedding method? And if you think about, the motivations for JL, one motivation is like, I have this high dimensional point set. I want to run some algorithm on it, like clustering, nearest neighbor search, whatever. If I just run the algorithm on the high dimensional version, it's going to be slow. It's going to use a lot of memory, whatever. But let's say it's going to be slow. So let me first project the data down to low dimension. And now my algorithm is probably faster because it's operating on lower dimensional stuff. So if you think about it, there are two parts to this. Part A is actually do the embedding. And part B is now run the algorithm on the lower dimensional version. So yes, getting the dimension low helps part B. But, it's not going to be worth it if part A is itself just as slow or slower. Ideally, I want both parts to be fast, both the embedding time and then running the algorithm on the lower dimensional version. So we've nailed the dimension that's achievable. We've basically nailed part B. We know that you can achieve 1 over epsilon squared log n, and there are some point sets, so we've nailed in the worst case, there are some point sets where you simply cannot do better than that by a constant factor, by more than a constant factor. So now the question is, can we now do something to improve part A, which is speeding up the actual embedding? So the history behind this, first there was Ocleoptus in, I want to say 2001. Sped up the map, z gets mapped to pi z by a factor of 3 without sacrificing the target dimension. So what do I mean by that? Pi is some matrix. What he did basically was, he looked at what was the target dimension that the best analyses out there could prove. It wasn't, he looked at even the constant factor. It's not just big O of 1 over epsilon squared log n. He figured out like what is exactly the constant hidden in that big O in the analysis. And he showed that you can achieve that same constant while making it so that the majority of the matrix is actually 0. In fact, 2/3 of the entries are 0 in expectation. So what he did was kind of pi ij was sort of plus minus 1 with probability, 1/3, 0 with probability 2/3. And you have to scale by something to make the calculations work out, but scale by something. Okay. Right here, I think for him, S was basically m over 3, something like that. Maybe. So with probability 1 over 6, you get a plus 1. With probability 1 over 6, you get a minus 1. So with probability 1/3, you get either plus 1 or minus 1. And then with probability 2/3, you get a 0. So in expectation, 2/3 of every column of this matrix is 0. Of course, if you just want 2/3 of the matrix to be 0, that's trivial to achieve if you're willing to blow up m by a constant factor, right? Just tack on, instead of making it m dimensional, instead of making it have m rows, make it have 3 m rows, where your last 2 m rows, you just make it all 0. Okay. Yes, now 2/3 of your matrix is 0. Okay, but you haven't really done anything. But with him, he actually kept m to be exactly the same, even up to the constant factor, and was still able to sparsify the matrix by a factor of 3. So that's really where the benefit is. And keep in mind now, why is this useful? Keep in mind that, again, just a fact about matrix vector multiplication, pi times z is equal to the sum I goes from 1 to d of zi times pi I, where pi I is like the ith column of the matrix. So the point is now, how much does it, you're basically keeping, you can think of it as you're keeping m counters around. You initialize it to 0. And in a for loop, you're adding zi times pi I to your counters, right? Does that make sense? So you keep adding this into your m counters, because this is an m dimensional vector right here. So if only m over 3 of the entries of pi I are non-zero, then this takes time. Yeah, how should I say it? Takes time roughly, let's say, m over 3 to add to my m counters. So you're kind of saving a factor of 3 there. I mean, of course, you have to be careful. I mean, depending on how this is being implemented, if you can do, some parallel operations on your computer, then maybe this doesn't really matter to you. But this could matter in principle, depending on the architecture of the machine that you're doing this on. Okay, so Ocleoptus was the first person to give kind of anything non-trivial. And after him, there was Ilon and Chazelle. in 2006. And they were the first to give an actual asymptotic improvement. So they could do z gets mapped to pi z in time O of d log d plus m cubed. So if you think of m as small, m is the target dimension. If you ignore the m cubed, this is nearly linear time in the dimension of the vector z. So it's like, what better could you hope to achieve? This is called the fast Johnson-Lindström transform. Fast Johnson-Lindström transform. Or the FJLT. We are going to talk about this. We might not get to it until Wednesday. But roughly what this scheme does is it says, okay, they say like, if my vector is very well spread around, if z is very well spread around, meaning like its mass is not fully concentrated in one place, but its mass is spread around. So let's say all the entries are the same or close to the same or something like that. Then they have a matrix pi that works. It's basically a sampling matrix who sample entries from z. Of course, a general vector z need not be well spread around. It could be a standard basis vector. You could have all your mass in one coordinate and everything else 0. So what they say is our pi is actually going to be a product of a few different pi's. Kind of the first matrix we're going to hit z with is going to be a random matrix that with high probability spreads the mass around so that z is, after you hit it with that matrix, it's with high probability not concentrated in just a couple coordinates. It's spread around. Then they say, now that we've done that, then we can apply the next matrix, and then that will work on this well-spread vector. So our final pi is just the product of these two matrices. Okay, so you look at this and you say, well, okay, what's the downside? The downside is, wait, what if z was actually originally super sparse? For example, what if z only had one non-zero entry? Then doing the dense matrix vector multiplication is actually not even that bad. If it only has one non-zero entry, that's basically just telling me some column of pi. So pi z is just zi times that column of pi times pi I. So it's very fast. It takes time m to compute pi z. So, but if you look at Eilert Chazelle, what they're saying with the FJLT is, I don't like sparsity because it kills the correctness of my procedure. So I'm going to densify the data first, and then I'm going to operate on the densified data. But that could be a serious downer for runtime. Like if your original data set was very sparse to begin with, I don't want to densify it. Densified is just making the data even more complicated. It's going to take now more time to do an embedding on it. I would like to take advantage of the sparsity to do better than this. And kind of the first paper that showed that you could do something with an asymptotic improvement for this was Dasgupta, Kumar, and Charlosh. This is 2010. And for people who don't know, apparently I don't speak Hungarian, but if you ever meet someone who speaks Hungarian or whose name is Hungarian, an S in Hungarian is like an SH in English. So it's not Sarlos, it's Charlosh. And if you see an SZ in Hungarian, it's like it's like an S in English, which is, I guess, contrasts with like Polish, where it's an SZ in Polish is actually like a sh. So anyway, just a random fact. So Dasgupta, Kumar, and Charlotte were the first to give some asymptotic improvement for sparse vectors. And then kind of the state-of-the-art bound is due to myself and Daniel Kane. And then we show that you can do z gets mapped to pi z in time, basically, of m plus epsilon m times the number of non-zero entries in z. So z naught for me is the support size. It's the number of non-zero entries in z. And the way that we achieve this, let me call this S. What we show is that can get a JL transform with S non-zeros per column. So pi itself is sparse, like Ocleoptus, but even sparser. Ocleoptus made it so that only a third of the entries are non-zero. Now we're saying that only an epsilon fraction are non-zero, right? So epsilon could be something very small. And this is called the sparse Johnson-Lillenstrauss transform. Or the SJLT. And actually, what is the matrix? The matrix is, I'll draw it for you. So if you look at each column of this matrix, you can basically break it up, the rows, into blocks. As blocks. And in each block, you're going to have a bunch of zeros and then a single one. And then a bunch of zeros. And that one is in a random location. I claim that you've seen this matrix before. Right? So what is this matrix?
It's like the coherent matrix for a code.
Yeah, okay, good. Yeah, so it is related to like how to take a code and convert the code into an incoherent matrix from the homework. But, a code could be, a code is like a code could be deterministic, right? A code is a deterministic object. It's a collection of vectors that has some overlap properties, right? Or distance properties. Here, this is not deterministic. I'm choosing where to put the ones randomly. So you could say, yes, it's like a construction of a random code. But I claim that exactly this kind of distribution is one we've already seen in class.
So related to like the Countman sketch?
Yeah, so it's exactly the count sketch. Oh, good. You're right. What I wrote is the Countman sketch. Because I have a typo, it should be a plus minus 1. Okay, so now it really is the count sketch, right? So each one of these non-zeros is a random sign. So what we show is that the count sketch itself actually provides the JL guarantee, where M is O of, we're going to prove it for a distributional JL, which implies JL. M is 1 over epsilon squared log 1 over delta, and S is going to be O of like 1 over epsilon log 1 over delta, which is O of epsilon M. Okay. And there's a lower bound by myself and Hui Wen, which says that there exists point sets such that M at most, O of 1 over epsilon squared log n implies some column needs at least omega 1 over epsilon log n over log 1 over epsilon non-zero entries. In other words, like, there are point sets where if you try to embed them with sparse matrices, if you try to tailor a sparse matrix just for that point set, it doesn't even have to be a random matrix. It doesn't have to be count sketch. There simply isn't a sparse matrix with sparsity better than this, which is almost what you would get from this SJLT up to this log 1 over epsilon term. So the SJLT is in the worst case nearly optimal in the sparsity it achieves. Okay, so let me show you now how to prove this. I think that will take up the remainder of the lecture, and then we can talk about the FJLT and move on Wednesday. So before I tell you how to prove, basically what I want to prove to you is not the lower bound, but what I want to prove to you is the upper bound, namely that this works. Okay. Any questions before I prove it? So let's prove it. SJLT analysis. So let me define some random variables. Eta are, let's just say that pi ri is equal to 1 over root s times eta ri times sigma ri, where eta ri is either a 0 or 1, and sigma ri is in -1, 1. So what I can, I just want to, this just makes it easier notationally to carry out the proof. What I want to imagine is that pi actually is a completely dense random sign matrix where the entries are sigma ri, but then I masked it with these etas. So if eta is a 1, I actually keep the sign. If eta is a 0, I zero out the sign, and I can express the matrix this way, right? Where eta is an indicator random variable telling me whether that entry is 0 or not. Does that make sense? And then if you look at kind of y, which is equal to pi times z, you look at the error random variable. So let's say now capital E is for error, is defined to be pi z L2 norm squared minus z L2 norm squared. And without loss of generality, I can just say, let's say z is 1. Because if it preserves vectors of unit norm, it preserves vectors of any norm because it's a linear map. So this thing here.
What's Ri?
What's Ri? So like R, remember pi is an M by D matrix. So like R is between 1 and M, and I is between 1 and D. Does that make sense? So pi Ri is just like the Rith entry of pi. Does that make sense?
Oh, I thought it was like R sub I. Sorry,
R comma I. If that helps. I just don't want to have to keep writing the commas. Okay, so this thing here is, so you can write, it's the sum over all I from 1, or R from 1 to M of pi z R squared, which is the sum, R goes from 1 to M. There's a 1 over root S squared, so there's a 1 over S. And then now the sum, I goes from 1 to D of eta Ri sigma Ri Zi squared. Okay. And this is equal to now, I'll write it like this, 1 over S, sum R goes from 1 to M, sum I goes from 1 to D of eta Ri squared sigma Ri squared Zi squared plus the sum goes from R goes from 1 to M, sum I not equal to J going up to D of eta Ri, eta Rj, sigma Ri, sigma Rj, Zi, Zj. Okay. Now, let's look at this. Let's take these two summations and like swap their order. If you swap their order, you get sum I goes from 1 to D, Zi squared, sigma Ri squared is 1, so that doesn't matter. Eta Ri squared is the same as eta Ri because it's a 0, 1 random variable. It's a 0, 1 variable, so if you square it, 0 squared is 0, 1 squared is 1, it doesn't change anything. So now here you have the sum over all R from 1 to M of eta Ri. What is this? Oops. What is this quantity? Can someone tell me?
Is it 1? Because it's just 1 in each column?
No. There's not 1 in each column.
Yes.
Oh.
It's S. There's S in each column, right? But yeah, close. There's not 1 in each column. There's 1 in each block. And there are S blocks, so there are S of them.
Yeah.
So this is S. So remember now, there's this 1 over S, and then there's this S. So that cancels. So this goes away. And the sum of zi squared is 1, right? But remember, there's a minus 1 here too. So that cancels. So that just goes away. So this implies that E is equal to 1 over S, sum R goes from 1 to M, sum I not equal to J, of eta Ri, eta Rj, sigma Ri, sigma Rj, Zi, Zj. Okay. Sounds like a mouthful, I know, but that's what it is. Okay. And by the way, I mean, it's interesting because if you look at Ocleoptus's original proof, right, or just like his construction, I mean, it's somewhat similar to this. By the way, I should say, so the count sketch indeed works. Another thing you can also do, and the same analysis we're about to do shows it, is don't do the count sketch. Just like for each column, pick S entries without replacement and make those S entries be random signs. So there's no more block structure. It's just simply S locations chosen without replacement randomly. Make those be random signs and make the rest be 0. You can prove via the same analysis we're doing now that that also works, okay? Which is very similar to Ocleoptus. Ocleoptus is basically, Ocleoptus says in each column, you know, pick the entries independently, decide whether or not they should be, you know, 0 or non-zero. And make the sampling probability be such that you expect S non-zeros. Whereas here we're saying, I don't just want to expect S non-zeros. I want to enforce that there are exactly S non-zeros, right? Because I'm sampling S without replacement. I'm enforcing that they're exactly S. That actually makes all the difference. You can prove that, you know, if you actually do Ocleoptus's version, where you just IID choose whether to make it 0 or non-zero, you actually need S to be 1 over epsilon squared log 1 over delta if you do that. But if you enforce this, then you can actually save on S by a factor of epsilon. So it's just the way that these random variables behave, that their tail downs behave, that somehow this very slight tweak is like all that it takes, but it's actually necessary to make the tweak.
And the version with the fixed number of ones is better?
Oh no, so the version with the fixed number of ones, which, you know, you can either choose without replacement, or you could do it like the count sketch. The count sketch also has a fixed number of plus minus ones per column. Those do strictly better than if you make it so that, you know, the entries are just IID 0 non-zero. Because the problem if you do that is, like, basically, I haven't convinced you that it's a problem, but you can see why there's a difference already in the analysis. Because for us here, the diagonal terms from that double sum perfectly canceled out with the -1, right? And the only thing that's left is the off-diagonal terms where I is not equal to j. But in the Ocleoptus version, the diagonal terms and the -1 do not perfectly cancel out, right? Because you only expect them to cancel out. You know, in expectation, that diagonal gives you 1, but there's variance there, and it probably is not going to give you 1 exactly. And if you try to understand the deviation there from the diagonals, that turns out to kill you already. Okay, so I'm not going to prove that here, but that's kind of an interesting thing where you might not have a priori expected that there would be a difference, but it turns out that there actually is a difference. Okay. So let's go on to the next board. Actually, let me switch back to black. So we just said that the error random variable is 1 over S, sum R goes from 1 to M, sum I not equal to J, of eta Ri, eta Rj, sigma Ri, sigma Rj, Zi, Zj. And let me remind you that we have the Hansen-Wright inequality, which we're going to use. Hansen-Wright says that for all, I'm going to write the norm version. You know, remember, tail bounds and norm bounds are equivalent. It says for all p greater than or equal to 1, if you look at the p norm of sigma transpose a sigma, where sigma has plus minus 1s, random plus minus 1 is the p norm. This is at most root p times the Frobenius norm of A plus p times the operator norm of A. Just remember that if you look at a random variable z, its p norm is just defined to be the expectation of z to the p to the 1 over p. So E, I can write E as sigma transpose, and then I'll call it, I'll call this matrix A sub, let's call it A sub z eta, or let's call it A sub eta, sigma. So it depends on eta. It also depends on z, where A is the matrix which looks like a 1 over S here, and it's a big block diagonal matrix. And let me call this matrix let's say Z1 transpose. This is A eta. Okay, so you know what? Let me not write it like this. I'm just going to write it as A eta 1, A eta 2, and then the number of them is S because they're S blocks, or actually M. A eta M. Each one of these is D by D. So this is a big matrix. It's MD by MD. And if you, what are these matrices? If you look at A eta R, and you look at the ith jth entry of this thing, it's equal to 0 on the diagonals if I is equal to j. Otherwise, it's equal to zi eta ri zj eta rj if I is not equal to j. So it looks a lot like, I'll call it z. I'll invent some notation. Okay, so this funny dot product thingy, what I mean by that is, these are two vectors. There's a vector z. There's a vector eta r, which is like eta r1, eta r2, up to eta rd. It's also a d-dimensional vector. I'm going to take these two vectors and entry-wise product them, okay? Which is basically a mask. Eta is a mask vector, right? It zeroes some things out, it keeps other things. So I apply this mask vector to z. So it zeroes out some entries of z, it keeps the rest. And then I take that masked version and I take ZZ transpose. And then I zero out the diagonals. Does that make sense? That's what A eta R looks like. Okay. Questions about this? Okay, so what do we need to understand? We need to understand the Frobenius norm of A eta and the operator norm. And let me also, there's two sources of randomness here. Sigma is random, but so is eta. Okay. So let me take the LP norm. Let's look at sigma transpose A eta sigma. Let me take the LP norm with respect to both, like, in other words, I'm taking the expectation with respect to both eta and sigma. Okay, so this I can write as, first I'm just going to do like, you can imagine here, like over here in this definition, the top right, there are two sources of randomness. So I'm taking it over both sigma and eta.
Z here has been rotated so that it's not sparse, right?
What's been rotated?
Z, so that it's not sparse.
What do you mean by Z is not sparse? Z is whatever vector I'm trying to embed.
Right. Well, I thought we were doing, there's like the pre-processing step where you make sure that the support is not too small.
Oh yeah, no. So that, yeah, sorry if I was confusing about that, right? There are these two approaches. There's this approach and this approach.
Oh, I see. Okay, sorry. I
Ilon
thought
Chazelle
it
does that
required that.
pre-processing. The sparse JLT, like just this is pi. That's it. Pi is the count sketch.
Got it.
Yeah. So basically, what I want to say is like I'm gonna take the expectation over sigma first, and then I'm gonna apply Hansen right. I'm gonna get an answer that depends on a eta, and then I'm gonna take the expectation over eta. So let me write this as let me write it like this: sigma transpose a eta sigma LP sigma, and then like LP eta. If that makes sense. So let's first just focus on what happens when you. So now like the eta is fixed in there, and I can just apply Hansen right to that. Okay. So next board. Let's go to the next board. So this is at most by Hansen up to a constant by Hansen right. Root P times the Frobenius norm of A eta plus P times the operator norm of A eta. And then LP over eta, take the randomness over eta. And then I can do, triangle inequality, and I can say, look, this is at most root P times A eta Frobenius norm, LP over eta, plus P times this thing, operator norm. So let's first do the operator norm, because that's, I think, a little bit easier. So remember, if you have a block diagonal matrix, then the operator norm is the maximum operator norm of any block. So we just have to ask ourselves, like, what's the maximum operator norm of any block? So the sup over all x of unit norm of some like x transpose A eta x is equal to actually, how do I want to say it? I can just write, let's just write this. This I think will be even easier. Good. Look, A eta is just actually equal to, and by the way, there's, the way I defined A eta is there is this 1 over S that's on the outside of everything. So A eta R, yeah, I mean, I guess unfortunately, so I didn't put 1 over S in the definition of A eta R. So we just have to remember to divide by S at the end when we do all this stuff. But if you look at A eta R here, this is equal to Z, funny dotty thing, eta R transpose, Z funny dotty thing, eta R, or sorry. Okay, but then you have to subtract off the diagonal minus the matrix that has like every entry, all the entries on the diagonal, which here is, Z1 squared eta R1, Z2 squared eta R2, all the way to like ZD squared eta RD. So this is what A eta R is. So the operator norm is the operator norm of this, which, you could use triangle inequality. You could even save a factor of 2 by doing something slightly fancier, but let's use triangle inequality. By triangle inequality, this is at most the operator norm of Z dotty thing eta R, Z dotty thing eta R transpose, plus the operator norm of this square matrix here, this diagonal matrix. What's the operator norm of this? It's basically, when we proved JL before, we basically ran into something like this. This is a rank 1 matrix. It has a single non-zero eigenvector, which is z funny dotty thing AR. So its operator norm is the L2 norm squared of that vector, which is at most the L2 norm squared of z. And this is a diagonal matrix, so its eigenvalues are just the entries in the diagonal. So this has operator norm at most z L infinity norm squared. So this is at most 1, this is at most 1. So we've just shown this is at most 2, right? And then remember there's a 1 over s that you have to remember. So this, this is basically always at most 2 over s. So you don't even need to consider the fact that eta is random in this part. We're going to use that for the Frobenius norm part, the fact that eta is random. But for the operator norm part, eta didn't even need to be random. Okay, now what about the Frobenius norm? Okay, so the Frobenius norm squared A eta Frobenius norm squared is equal to one over s squared, because there's a 1 over s over on the outside, so square that. Sum r goes from 1 to m, sum I not equal to j of z I squared, z j squared, eta ri, eta rj, where, again, the etas should be squared, but it doesn't matter because it's a 0, 1 variable. So squaring is 0 is 0, squaring 1 is 1. You don't have to square the etas. Now notice that zi squared, zj squared doesn't depend on r. So you can just take these and move them in here. So this is 1 over s squared. Sum r goes from 1 to f. Sum I not equal to j. Yeah, let's also reverse the order of summation, I guess I should say. So reverse the order of summation. Sum I not equal to j, zi squared, zj squared, and then like a sum of r goes from 1 to m of eta r, eta ri, eta rj. And let's just call this thing here now like qij. What does qij mean in words? Qij is like, if you look at the ith column of the matrix pi and you look at the jth column, how many non-zeros do they have in common, right? How many rows do they both have in common as being non-zero? And then now if you look at, okay, so let's just recap. So what do we have? We're almost out of time here, but I can basically tell you how to finish this. So what I said is eta Frobenius norm squared is equal to the sum 1 over s squared, the sum I not equal to j of zi squared, zj squared, qij. And what we're interested in is we're interested in A eta Frobenius norm LP eta. What does that mean? That means the expectation, that means the expectation over eta of this Frobenius norm raised to the pth power all to the 1 over p. I'm just going to view that as, this is actually like the square raised to the p over 2th power, right? That's the same thing. And then raised on the outside to the 2 over p to the 1/2. Right? So a lot of funny acrobatics here. But basically the point is, this is the same thing as, basically what I'm saying is this is now A eta Frobenius norm squared, and then LP over 2 eta. So I have P has to be at least 2 so that this is still a norm. And then I can square root it all at the end. So I don't have to worry about the square root until the very end. So now the point is, I basically want to know the norm of the Frobenius norm squared. And then I can use triangle inequality. This is at most, so I have a 1 over s squared, but there's a square root on the outside. So this is 1 over s times the sum I not equal to j of zi squared, zj squared, and then the norm of qij. That was just triangle inequality and using what I wrote down as the Frobenius norm squared. And then I'm not going to do it, but the point is, what is Qij? What can you tell me about Qij? It's basically like a binomial distribution, almost, right? Because it's like, you know, I have these m trials because there are m rows, and I'm asking, of these m rows, how many times do I have a non-zero for both I and j? What's the probability that for a given r, what's the probability for a given r, I have a non-zero for both I and j? It's roughly s over m quantity squared, because there are s non-zeros out of m rows. So it's s over m times s over m, which is s squared over m squared. So what I'm doing basically is I'm looking at this looks a lot like the binomial distribution with parameter s squared over m squared, where I'm summing up Bernoulli's p, where p is s squared over m squared, and I'm summing it m times. Qij is roughly a binomial distribution like this. Does that make sense? So again, I'm basically out of time. Why is it not exactly a binomial distribution? It's not because they're not independent, right? The etas are not independent, right? You know that there are exactly s per column. So for example, if you know that, you know, rows number 1, 2, 3, 4, 5, 6 are both non-zeros for I and j, then that decreases the chance that the future rows are both non-zero because there are less of them. There's only s total, right? So it's not exactly a binomial distribution, but you can show it's not too hard to show. I'll put it in the notes that the moments are still bounded by the moments of a binomial distribution. Then you try and figure out what are the moments of a binomial distribution. You get something, you plug it in, and you get a bound. Okay, so then you're done. You have a bound on the Frobenius norm moments. You have a bound on the operator norm. You plug it into Hansen-Wright. That gives you a bound on the moments of the error random variable. And then you plug that bound on the moments of the error random variable into Markov's inequality, right? So now you can set P, right? Remember now, the probability that the error random variable, this is the last thing I'm going to write before I let you go, the probability the error random variable is bigger than epsilon, which is what you're trying to bound, is at most, it's at most 1 over epsilon to the p times the p norm raised to the p. This is just Markov. And then now that you've bounded this thing, that's what we've just done, you can plug it in and you can basically get exactly what I told you. And, you know, at this point, it's just really a calculation and we're out of time anyway. So I'll put the exact details of that calculation in the lecture notes, but that's all there is to it. Any questions?